Hey, hi Rajesh, good morning.
Hey, good morning, Jonathan.
We'll start in just 2 minutes. Okay, let others also join in.
Yeah.
Rajesh will start in just 2 more minutes. Okay. All right, guys, let's start. I think it's already 9:05 and people are not turning up. Okay, nonetheless, let's start. So today we'll do some pending applications from NLP. So let me just import, say, some of the basic libraries. Support pandas also, and maybe NLTK as well. Okay, and I'll also import matplotlib. I might be plotting a few things. Okay. All right, before we start, if anyone has any questions, you too can ask if you have any questions. Any questions as such, people? Shall I go ahead? What do you recommend? Or shall we wait? Requesting to be please interactive. Yeah.
Yeah.
Okay, I'll go ahead then.
Yeah.
All right. So we are going to see some interesting applications of NLP today. We are moving towards the advanced NLP side. So the first application that we'll see today is word sense disambiguation. Okay, or simply called as WSD. The idea is English being a very ambiguous language, we want to see the meaning of a word for a given sentence. Okay. So imagine you're given a sentence or a paragraph, and from that text, you pick up a word and you want to know what meaning does it convey. Because like any English word can convey many different meanings in different contexts, in different sentences. Okay. So we want to figure out the meaning of a word. We want to disambiguate the meaning. Okay. For example, if you think of the word report, I mean, report can mean many different things. You are reporting to someone or you are preparing a report. Think of the word, say, book. So book can be like a handbook or a book that you read. Okay. It could be that you're booking, say, a ticket, or it could be that, let's say, maybe say another thing about book would be, I think these are the two generic contexts that you can book a ticket or you're reading a book. Maybe think of the word, say, bank. So it could be money bank, river bank, and so on. Okay. It could mean trust also, that let's say I bank on you. So one word can convey many different meanings. So for this, we need an algorithm called as LESK. Now, there is no full form for this LESK. This is just named after the scientist. I think his name was Michael Lesk, who built it in, I think, some 1970s or 1975s, somewhere closer to that. But the algorithm is still used. So we'll use the LESK algorithm. To use this, you need to download a few packages. So I have some pre-existing notebooks, which I'll use directly. So to install this LESK, you need to download the following two things. Okay, you'll have to install the WordNet library. This library contains the meaning of like the multiple meanings for a word, and this is the LESK algorithm which disambiguates. Okay, using the meanings. So once you have installed it, okay, in my case it is already installed. So what you can do is you can take a sentence and so let's say the sentence is maybe say I'm going to a bank to make a withdrawal. Okay. Or maybe say to get some money. Okay, let's say simply like this. Okay, and here I'm interested in the word which is, say, the bank. Okay, so give me the context for this word bank. So what you can do is, let me just show you. Give me a sec. Yeah. So to use this, let me just use this LESK algorithm. Let me see in which library it is. Yes. So what you have to do is you have to import this LESK from this word sense disambiguation class. So import LESK here. Okay, and then you have to convert this sentence into tokens. So I'm going to convert this sentence to tokens using the word tokenize function from NLTK. Okay, so you can import from NLTK this word tokenize function. So apply this word tokenize. So just to show you, you apply this word tokenize to your sentence and it will break it to tokens. Okay, it will break it to tokens. Okay, so this has broken it down into tokens. And now what you could do is to get the meaning of the word. Okay, you apply this Lesk algorithm. You give the sentence and the word. You can just type the word bank here. Okay, so we are looking at the word and let's see what it prints. Okay, so it says that it's a synset. Okay, what a synset is, it's a collection of two things. Okay, it has you can say the definition of this. So I'll just show you. Let me take this synset. Okay, I'm going to take this synset. It has two things. One is the definition. So definition would mean what is the meaning of the word in this given context. Okay, so if you look at this definition, it says that a container for keeping money at home. So here the word bank means that, I mean, the way it is interpreting is that so if it's like what we say is a money box. Okay, that is what it is interpreting as, this word bank. Okay, so the title is given to it as a savings bank. Now you can actually look at other examples. So some other examples are also stored which have the same definition. So if you want to look at other examples which have the same definition, you can simply type examples here and it will give you some examples. So it is saying that the coin bank was empty. So this sentence and this sentence, okay, essentially they convey the same meaning for a bank. Okay, this sentence and this sentence convey the same meaning for a bank. Okay, I hope you get the point. So you can do it for any sentence. Okay, you can do it for any sentence and the corresponding word, and it will generate the meaning and some examples for it. And with the help of newly generated examples, or let's say with the help of definition, you can disambiguate the word. Now, there are a few things. Maybe you would like to know what are the different, let's say, meanings for the word bank. What are the different synsets that are stored? So you can get the different synsets also. Just give me a sec. Yeah, here is it. Yeah. So you can get the different synsets. Okay, so you can get all meanings. Okay, all possible meanings of the word, say, bank. Okay, let me just say all possible meanings of bank. All right. So I'm printing. First of all, let me show you what are the all possible synsets and what are their corresponding definitions. So this will print. Let me just show you this. Okay. So this will print all the corresponding synsets. Okay. Just a second. I haven't imported this. Okay. So do you see these are the different meanings of the word bank. These are all possible synsets. And now I'm simply running a for loop to see the definition of each of them. Okay, I'm simply running a for loop to see the definition of each of them. Let's see this. Okay, I've already imported this. Okay, so these are all possible definitions for this synset. It means that, okay, it's a sloping land, essentially maybe a river bank. Okay, this is a depository financial institution which accepts money like the regular bank. This is, it means a long ridge or a pile. I have no clue. Maybe that is also called as a bank. Okay. An arrangement of similar objects in a row or in tiers. Okay, that's also called as a bank of objects. Okay. I mean, you can see there are so many meanings of this word bank. I mean, instead of me describing everything, these are all possible meanings. Okay. You can check for different possible words. Let's say I'm going to show you for the word, say, report. Okay. So every word has many different meanings. So you can use, okay. So these are all possible meanings for the word report. Okay. So this way you can see what are the possible meanings and try to disambiguate it. Now, one caveat is this. Okay. Let me just show you. So please note this, LESC works better, okay, when you provide the parts of speech. Okay, when you provide the parts of speech. So just to give you an example, okay, let's say that, okay, okay, let me think of a sentence, maybe say, okay, let me think of the sentence, and the sentence is this. Okay, you should be, yeah, so you should be able to live with dignity. Okay. Okay. You should be able to say code. Okay. Let me put it this way. All right. So here, if I ask you what is able here, what would you say? Which parts of speech it is? Which parts of the speech it is?
Well,
It's a verb, right? Or let's say if I write one more sentence, let's call it sentence one and say sentence two. Okay. And let's say you are an able programmer. Now, what is this now? What is able now?
adjective.
It's an adjective. Okay. So let's see if LESC is able to work for us. Okay. So let's use the LESC algorithm. Okay. Let's get this inset. So I'm going to print both the things. So let me first do the tokenization of this word. Okay. So I've tokenized the sentence one, where the word is able. Okay. Where my word is able. Okay. I'm tokenizing the sentence, passing the word, and let's pass it as it is. Okay. Let's pass it as it is and look at the definition. Okay. Look at the definition. So it means that have the skills and qualification to do things well. Okay. And this is all right. I mean, it makes sense, right? Yes or no?
Yes.
Okay. Now let's see for sentence two, what does it say? It says that you are an able programmer. So in this case, if you look at sentence two, what it is doing is that, I mean, is it saying that having a strong, healthy body? I mean, does it make sense here? No, right?
No.
Okay. So here, this in sentence two, it is not working well. So what we will do is we will try to get the parts of speech for this word able. Okay. So the one way that you can do parts of speech tagging is you can take NLTK and you can import the POS tagger from WordNet, and you can pass the. I'll just do this later. Okay. So we can pass the word tokenized sentence. Okay. I'm doing it for sentence one first. Okay. So if you look at this, what is able right now? Here it says it's an adjective. Okay. You should be able to code. Here it says that it's an adjective. Okay. But it seems that, I mean, would it be an adjective? Probably not. Maybe POS tag is not working. It should be a verb, right? If you think about it.
Yes.
Okay. Okay. Anyways, let's try with an adjective first, and let's see what it returns. Okay. So I'm passing the parts of speech as an adjective. Let's see what it returns. Now, don't you think it makes more sense? Having the necessary, because you should be able to code, right? You should have the necessary skills or know how the authority to do something. Yes or no? In this case. And here also, I mean, I should maybe. Oh, we are doing it for sentence two. My bad. We are doing it for sentence two. Let's do it for sentence one. It has basically the same meaning for the same parts of speech. Okay, let me do it for sentence two, and let's see what it. Here also it should return an adjective in my. So here also it returns an adjective. So maybe POS tag is not working well. Can you think of maybe rewriting this able here so that we get say a verb here? Maybe change this sentence slightly. So POS tag is not working well here for this example. It should be a verb. I agree. It should be a verb. Maybe give me another sentence where we can look at the differences. Okay, let's see. My vocabulary is not that great. Anything comes to mind? Not just for this sentence, maybe for another sentence where maybe say a word has different parts of speech. Can you think of two sentences? And let's try on that. So here it will say the same thing because part of speech is the same. Okay, let's think. Okay. Let's see. Okay, let's see. Okay, let me put some sentence here where we can give, or maybe rather I'll ask. Okay, Google. Okay, that will be nice. Okay. It's giving her a definition. I mean, Lesk is more towards the parts of speech. Okay, okay, I'll just take the simplest examples. Let's say I will report to my manager. Okay, and I'm writing a report. Okay, so this is the word report here. So if you think about the parts of tag for sentence one, what is this? It's a verb, right? Does that make sense? It seems to be a word, verb. Okay, you can see that it's a verb. Okay, so let me pass the verb to it. Okay, and let's see what does it. So it means that you make known to the authorities, and it makes sense here, right? Yes or no?
Yes.
It makes sense here. And let's say I'm writing a report. So let's do it for sentence two. Okay. So I'm writing a report. So report would be probably a noun here. I'm not sure though. Yeah, it seems a noun. And then you can use the same. Okay. Yeah, the act of informing by verbal report. Okay. No, but is it the same? No. These are different things, right? Or are they the same? The act of informing by verbal report. I mean, this makes sense. Make known to the authorities. I report to my manager. Okay. This I'm not sure. Okay. Let's see what are the different meanings of this word report. Okay, here it is. Which do you think would be more appropriate for the second one? I'm writing a report.
Second one. On the
Second
top.
one?
On the top, yeah.
The first one, right? Written document describing.
Yeah, appropriate is the first one.
Appropriate to the first one, but it is printing the second one. Okay. So maybe, I mean, this one is also, see, it was developed in around 1970 something. Okay. So it's not that great, but it is still used to disambiguate words to this day. Okay. It's not working that great, but it is still used. However, people have actually replaced it with the transformers, which are, I would say, excellent in understanding natural language text. That is why you use like softwares like ChatGPT, which can do a lot of tasks very well. Okay, but this is what people used to do for traditional NLP. Okay. Anyways, this is what it is. Okay, so this is your LESC. We'll do maybe one more. So let's say that, okay, we are working with a data set. Okay. Yeah, we work with, say, this tweets data set. Yeah, I'm working with this tweets data set. Let me just import this first. Have you seen this tweets data set before? Maybe in the last class?
That airline tweets, right?
The airline tweets. Okay, let's use this. Essentially, we are doing the embeddings. So generating embeddings for, and I would say generating low dimensional embeddings like from text. Okay, that is what we are looking at. Okay. So one of the ideas is I've just imported this data set, printing the first few, you can say, rows of this data frame. Essentially, my text is here. Okay, essentially, my text is here in this text. Okay, these are all the tweets, and the sentiment is here. Okay, and the airline sentiment is here. So this is the sentiment expressed. So for each text, you have, the answer to be negative, neutral, or positive. Now, if I convert this to a structured representation, it would be highly sparse, and what we say is, high dimensional, right? Yes or no? So if I convert it to structured representation, so just to show you, okay, this is, I'll use only a few of the tweets to expedite it. Okay, so I'm going to use maybe, say, the first, say, 1,000 tweets. I'm not removing any stop words, not doing any stemming lemmatization. This is just to show you. Okay, so let me use, say, the first 1,000, or maybe first 100 is more than enough just to demonstrate. Okay, so these are the first 101 rather. If you want the first 100, these are the ones. Okay, so once you have these first 100 tweets, I'm going to convert it to a structured representation. So basically, I'm trying to find each individual word and making a column for that. And I'm going to encode it. What do you want me to encode it with? Presence, absence, the count of a word, or TF-IDF? What shall we do? And give me a way to encode it. Okay, which technique shall we follow? We have seen all the three, I think, before. So shall I encode it with presence, absence, or say count of the word, or maybe say TF-IDF?
Presence, absence.
Okay, so if you want to do it with presence, absence, you can do transaction encoder. Okay, if you want to do it with the count, that is count vectorizer. If you want to do it with what we say, the TF-IDF, then you have the TF-IDF vectorizer. So I'm going to do it with the presence, absence, which is there in machine learning extensions. So go to ML extend, go to pre-processing, import this transaction encoder. Okay, import this transaction, instantiate it. So instantiate this transaction encoder. Okay, so the input to the transaction encoder is a collection of strings. Okay, is a collection of lists. Okay, it's a collection of lists. Now, if you see, what would you say it is right now? It's a collection of strings. So you have to make it as a collection of lists. So I'm going to make it as a collection of lists. So I'm going to split it by, let's say this. Does that make sense? I can split it by spaces, right?
Yes.
Okay, so this is just to show you. You should rather use the word tokenize first. Okay, please use the word tokenize function. I'm going to put everything to lowercase. That way, it will be, let's say if there is a word capital I and small I, they'll be treated the same way. Okay, so I put everything to lowercase. If you want, you can split this @ in front. Okay, maybe I'll do that as well. Okay, let me say. Or maybe I'll just replace wherever this @ is. Okay, so you can see I've replaced @. Okay, so these are the words that I have. I mean, if you want, you can do. I mean, word tokenize and then remove the stop words. I'm not doing that. This is just for a demonstration sake. Okay, so I'm going to fit it to this data. Okay, I fit it to my data. The transaction encoder is fit. If you want to see the unique columns, the unique words, these are the unique words that you have. Okay. So there are some hashtags also in this. So if you want, you can remove the hashtags. Okay, let me just remove the hashtags also. Just give me a bit. Okay, I removed the hashtags. If you see, there will be no hashtags anymore. There will be no hashtags anymore. Okay. Anyways, these are the unique columns. You should definitely do stop words removal. Okay, I'll make a note here. Okay. Do you want me to do it right now, or you guys can do it? What do you recommend? Shall I do it again? We have seen this before. What would you prefer? Shall I do this again? Tell me, please.
No, can't be done.
Okay, all right. Okay, all right. So once you have the stop words, once you have removed the stop words, you can encode this text. So you can transform this using the transaction encoder, pass the data that you had. So this was the data that you had. Okay. So you have to pass this whole stuff again. Okay. And this has been encoded to a string of true false. You can convert it to integers. Okay. So convert it to integers. Okay. 0 means absence, 1 means presence. And now I'm going to make it as a data frame. Okay. And column names will be t.columns. Okay. So it has been converted to a data frame. Okay. You can see that. Okay. There is some double quotes. Okay. I'll strip these double quotes also. Just give me a second. Okay. This is necessary. Okay. I'll strip these double quotes. And maybe single quotes also if there are any. Okay. Okay, you can see I have no, there is this still. Okay, this is maybe a special symbol. It's not the regular double quotes that we have. Okay. So these are some give me a sec. Anyways, this is fine. I hope you get the point. Okay. I mean, there are a lot of special symbols that you have. Like for most of them, you can see that the double quotes have been stripped. Okay. Single quotes are for what we say is denoting a string. Okay. You can see that most of the double quotes have been stripped. This may be a special double quotes. Okay. The formatting was a little off. Okay. And there are different fonts, right? So where is it? I don't know. And there was there with something. I think it was there before easy. We saw it somewhere, right? Was there next to E. Okay, but anyways, there is this double quotes there that you can just paste it and then strip it as well. Okay, so now you encode it. Okay, give me a sec. Oh, I have to pass that thing again. This is the problem. Just a second. I need to pass this whole thing again. because otherwise it will throw an error because some of the extra characters are there. All right, this has been encoded. Let's pass this whole thing again. Okay, so the encoding has been done. You can see that wherever the word is present, it's a 1, otherwise it's a 0. Okay. There is a blank space also somewhere, so that's why you see there's a blank space somewhere. That's why formatting is needed. Okay. All right, so this has been done. Once, I mean, if you see, there are a total of 730 columns right now. Okay, there are a total of 730 columns right now. So, and it's a very sparse representation because there are a lot of zeros. So, one idea is that I can make it low dimensional and dense. Okay, I can make it low dimensional and dense. So, this can be done using what we say is feature extraction techniques or dimensionality reduction techniques. Okay, these are called as feature extraction techniques. Feature extraction techniques. So you can use these feature extraction techniques. I'm going to show you some. I think I've shown you already. Did we do PCA before? Have we done PCA, principal component analysis?
No,
Have-
PCA we
Have we done the implementation of it at least? No?
PCA we have not done.
Okay, all right, let me show you. So there is in sklearn, there is this decomposition technique. Okay, and you can import this principal component analysis, PCA. You can specify how many dimensions you want. Okay, so currently you have 730 dimensions. So pick a number which is say less than the minimum of these two. Okay, it is important that the number of dimensions that you are choosing has to be less than the number of rows and the number of columns. Okay, so I'm going with say 50. So a number of components is 50. Okay, number of components. So these are the, so basically what you are doing is you are converting this 100 cross 730 data to 100 cross 50. Okay, so let's call this as say PC. Okay, instead of calling it as PCA, let's call as RED. Okay, and now I'm going to or maybe say your application. Okay, and now I'll apply this method to my data, which is in, let me store it. Okay, let's call it as the encoded data. This is the encoded data. Okay, so I'm going to apply this on this encoded data. So if you apply it, okay, number of components. Okay, so it has fitted, and so what it does is it finds out the new dimensions for your data, and if you want to transform it, you can apply the transform method. Okay, you can apply the transform method on this encoded data, and it will give you a new data of 100 rows, of 50 columns. Okay, do you see that the data looks like dense? There are no zeros anywhere, or very little zeros are there. Yes or no? So if I show you the shape of this would be 100 times 50. Make sense? So this is one algorithm which you can use to reduce the, you can say, number of dimensions of your data. Okay, and this particular algorithm does linear dimensionality reduction. Okay, this is linear dimensionality reduction. So just to give you an idea of what this means, the idea here is, so imagine I give you this data of say 100 times 750. Okay, and you want this data of say 100 times 50. So can somebody tell me if this matrix is say X? Let's say if this matrix is a X, what should I multiply X by? Okay, what should I multiply X by so that my resultant, you can call it as transformed X. So my transformed X becomes 100 times 50. So what should I multiply this by? Let's say this matrix is P. So what should be the size of this P? Any guesses?
50 into 50.
750 into 50. So this PCA determines this 750 times 50 matrix. Is this clear? Is this clear? So the purpose of PCA is to determine this 750 times 50. Okay, so it's trying to determine this. Okay, it's trying to determine this. Now, how it does it? There is a whole, big theory behind it. It's not in your syllabus. I mean, if I will start describing it, it will take me the whole lecture about the theory of this. I don't want to dive into this because it's beyond the coverage. But the idea is that you can use this. So currently, I want you to see every. So I'll just give you a small idea. Okay, let's say this is my data, and the data is like this: A1, A2, and so on till A750. Okay, so this is sample 1. Okay, in your X. Okay, this is sample 1 in your X. So this is your matrix X, and this is sample 1. Okay. Similarly, there would be another sample which would be say sample 2, and this would be say B1, B2 up to say B750. Is this clear? Like I'm just representing X with some generic numbers.
Yes.
I want you to see what P is. Okay, I want you to see what P is. So P has 750 values, right? Yes or no? P has 750 values along the rows. So I want you to focus on the first, the first column. The first column, here the first column in P. Okay, let's call this first column in P as maybe say P1. Okay, I'm going to call this as P1. Okay, so this first column in P, this P1 column, let's say this is Z1. Okay, and this is say Z2. Okay, and similarly, the next value is say Z3. We are only looking at the first column Z3. Okay, so how many such values will be there along the columns? Along the columns, how many such values will be there?
750.
750, right? Okay, so this will go up to around 750. Okay, let me just say dot dot dot, and it will go up to say 750. Z of 750. Now this is for the first one. Similarly, there would be there for P2 as well. Yes or no?
Yes.
Similarly, it would be there for P2 as well. Okay, all right. So let's say this is P2. Okay, and similarly, let's say this is some, let me call it as say O1. Okay, and say this is O2. Okay, and so on. Okay, and it goes up to let's say O750. Okay, I want you to visualize what happens in this transform data. Okay, I want you to visualize what happens in this transform data. Okay, so if you look at this transform data, what would be the first value in the transform data? If you know matrix multiplications, so what would be the first value here in this first row? What would be the first value here? The very first value. There will be how many values in this row? Let's say this is say M1, this is M2. How many values will be there? M50, right?
50.
Okay, I wanted to focus on the first value. What is this M1 here? Okay, what would be M1? Any guesses? So can I say M1 would be, okay, A1 times Z1 plus A2 times Z2, okay, plus A3 times Z3, and so on till A750 times Z50. Does this make sense? Yes or no?
Yes.
Okay. Now, what is essentially the column, the very first value in this column M1? Can I say it's a linear combination of my original values? Yes or no?
Yes.
This is a linear combination of my original values, and whose linear combination it is? Can I say it is nothing but depending on this P, the very first P column?
Yes.
This is defining the linear combination, right? So A1 into Z1 plus A2 into Z2 and so on. See, I know this, right? A1 to A750. What I do not know is Z1 to Z750. So if I know this, I can get the transform data. Do you think for the next row, if I figure out the next value, for the next sample, look at the next sample, okay? Let's say this one is some T1, T2 up to T50, okay? This one has T1, T2 up to T15. Do you think Z needs to change? What about T1 now? What would be T1?
B1 Z1 plus B2 Z2.
So can I say that this whole column of where you have M1 and T1, okay, let's give it a name. Okay, let's give it a name. Sorry. Okay, let me just give it a name. This first column, which you see right now, yeah, let me just give spaces here. This first column, let's call this column as maybe say transformed X1 or maybe say transformed feature 1. Okay. If you think about this first column, which is transformed feature 1, can I say the coefficients of this are in P1? Yes or no?
Yes, yes.
Similarly, for transform feature 2, the coefficient would be in P2.
Yes.
So can I say that all the 750 dimensions, they have been projected to these 50 dimensions with the help of these 50 columns, P1, P2 up to P50? Does it make sense? So your original data has now been projected with the help of a, see, what will be Z1, Z2? They will be real values, right? There will be some numbers, right? Numeric values. Yes or no?
Yes.
So if these are number values, can I say it's a linear combination? Yes or no? If these are real values, can I say it's a, linear combination? Now think of this. If I gave you some, maybe say, square features. So if this was A1, I make another feature which is say A1 squared. Okay. Now what would you call this? Can I say this would be
Polynomial.
Non-linear?
Yes.
Okay. Now essentially what you are learning is a linear matrix only. See, you will still be learning this P, right? But now you have non-linear features. So can I say you are now trying to reduce the data in a non-linear decomposition way? Just the features are non-linear. You have seen it in linear and polynomial regression. Yes or no? Where it is still linear regression, but you generate polynomial features.
Yes.
Okay, so it's the same concept here. You can generate even polynomial features. Okay, you can generate even polynomial features. But if you want to generate polynomial features, okay, there the name is different. It's not called as PCA, it's called as kernel PCA. Okay, it's called as kernel PCA. So this is non-linear dimensionality reduction technique. So it depends on what type of kernel do you want. So you have to define a kernel. So let's say I'm defining this kernel to be say quadratic. So poly kernel with the degree 2. Okay, so this is a quadratic kernel. Okay, so it will also give you a resultant shape would be again 100 times 50. Okay, I'll just show you the resultant shape. You can directly apply this fit underscore transform method here. Okay, and I'm printing the shape of this. So this would be 100 times 50. Do you see that? So we have used a quadratic kernel. Okay, so basically, essentially, we are looking at the quadratic of features, and then we are decomposing this into 100 times 50. Is this clear?
Yes.
Okay, so it's the same concept that we had used over there, but now it has been elaborated for dimensionality reduction. Now, I understand the bottleneck is how do you get this P? Okay, this is where you have a new optimization technique and a new way to decompose it. Okay, a new way to decompose it that I'm not discussing. Okay, if you're interested, I can talk about some hints. If you are really interested to explore more on this, explore singular value decomposition. Okay, and this is how it is. This thing is done. Have I spoken about singular value decomposition?
Yes.
So it's the same technique which is used. Okay, the same technique which is used. So you can use it here to decompose for kernel PC as well as PCA. Actually, SVD is a generic form of decomposition. It can be applied to rectangular matrices. Okay, it can be applied to rectangular matrices. Okay, in PCA, even though we are looking at the decomposition of this, right? What's the name of the method? I'm calling it as this ENC data. What is the size of ENC data right now? 100 times 730, right? If you remember it. Okay, I'll just show you the size of this. It's 100 times 730. Okay, 100 rows, 730 columns. So currently what, you may be thinking that it is trying to decompose a rectangular matrix. PCA actually works on the decomposition of X transpose X. So if this is X, PCA will actually decompose 730 times 730. Okay, so PCA does it on a rectangular matrix. SVD does it on a PCA does it on a square matrix. SVD can be applied to even rectangular matrices. Okay, so you can say that PCA is nothing but an extension to SVD, nothing special. Okay, maybe I'll give you some hints. Do you remember SVD to some extent? Do you guys remember SVD to some extent?
Yes.
Okay, so
That
maybe, yeah, maybe I'll I'll talk about it. Okay, so let's see this. So SVD is so let's take a rectangular matrix. I'm going to take a rectangular matrix, maybe say of the size A comma B. Okay, so what SVD will do, it will break it down into three matrices: U, sigma, and V transpose. Okay, do you remember the dimensions of U, sigma, and V transpose? Anybody who does?
It was N into K, K into D,
Okay, that's-
and D into N.
Okay, let's say I'm showing you what it would be. So it would be A times A, then it would be A times B, and then this would be B times A. Yeah, it would be B times B. My bad. Do you remember this? And then we use the top K vectors from sigma,
Yes.
and then so that's why we say the resultant number comes out to be A times K, and then this would be K times K, and this would be K times B. Yes or no? After picking the top K vectors from sigma.
Yes.
Okay. Okay. I'm going to give you now some hints why SVD is an extension to why SVD is generalized form of PCA. Okay. So when you're doing PCA, right? Okay. When you're doing PCA on any matrix. Okay. So let me first tell you what is actually U. Okay. So when you're doing PCA on any matrix, so can I take PCA on A times B? Can I take PCA on A times B? I'm doing PCA now on A times B, the same matrix. Okay. I'm going to show you how it is different. Okay. So when you are talking about U, right? So this matrix U, when you're doing PCA on this, okay, paste it here. When you're talking about U, this is also called as left eigen vectors matrix. Okay, it's also called as left eigen vectors matrix. So what you are doing is essentially you are doing this matrix A times B. Okay, whatever this matrix is, you are doing the transpose of this. What would be the transpose of this matrix? A times B. It would be B times A. Does this make sense? Can I say this would be A times B transpose? Multiply this matrix with itself. So this would be A times B. Okay. And now you are doing the eigen decomposition of this. Okay. Now you are doing the eigen decomposition of this. Okay. You're doing the eigen decomposition of this matrix. So this is your U. Okay. This is your U. So I want you to please understand this. This might become a little tricky for some. Do you guys know what eigen decomposition is? Anybody who knows eigen decomposition here? Do you know how to compute eigen vectors and eigen matrices? Eigen values?
No.
I mean, if you have taken a maths course specifically related to matrix algebra, so it will be easier for me to describe this. See, it's not in your syllabus, but if you know about this, then it will be handy for me to describe the next few steps. Is there anyone who knows what eigen decomposition is? What are eigen vectors? What are eigen values? Otherwise, it will go over your head. I have to start from matrix factorization. This is not in your course, by the way. So I have to describe what eigen decomposition is. I have to describe what factorization is. This thing also I have to describe in detail how SVD works. That is why I'm not going there. Do you guys know what eigen decomposition is? At least this much. No? Is there anyone who knows about it? Okay. I mean, you haven't solved, this is a common question. If you have done, say, a degree in computer science or maybe IT or any relevant branch, even in ECE, eigenvectors and eigenmatrices are taught. Okay, maybe it's a long time for you guys. All right, I'll give you some hints at least, okay, so that when you are reading it, you remember it, okay? So if you want to do eigen decomposition of a matrix, it has to be a square matrix, first of all. Okay, it has to be a square matrix. It cannot be a rectangular matrix. Okay, so if it's a square matrix, let's say this matrix is of size say B times B. Okay, I'm probably going to help you recall if you have done it in prior. So if this is a B cross B matrix, let's say I'm taking an example of say 2 cross 2. Okay, I'm taking an example of 2 cross 2. Okay. So this is A1, say this is A2, and let's say this is B1 and this is B2. I don't know whether you remember this or not, but this is quite common. This is taught in like all like undergraduate degrees, in even in BScs and all that. Okay. So what we do is we subtract lambda. Okay, we subtract lambda from the diagonal entries. Now, can you recall it if you have done it before? Anybody who can? Anybody who remembers now? Okay, if you find the determinant of this matrix, in terms of lambda, what kind of equation it would be? Do you know how to find determinant of a matrix? So again, to describe this, I need you guys to know if like if determinant is there. I mean, if you know how to compute the determinant or not. Okay, do you know that, okay, if I want to compute the determinant, you multiply for the 2 cross 2 matrix, I multiply these two values along the diagonals and subtract A to B1 from it. Do you remember it? So if you want to compute the eigenvectors of this matrix, you compute the determinant and set it to 0. Okay. If you set it to 0, it will come out to be a square quadratic equation in lambda. So there will be 2 roots. Okay. There will be 2 roots, 2 values possible for lambda. Okay. Those are called as eigenvalues. Okay. Those are called as eigenvalues. And then for an eigenvector, if you want to find out the eigenvector, see, I don't want to go there. I mean, you guys don't have an understanding of matrices, so this would be really difficult. Okay, you remember it like this. Okay, you guys please remember it like this. It's not in your syllabus, first of all. Okay, I'm just giving you these extra details. When you are doing simply PCA, remember that, okay, it's a linear decomposition. If you are doing SVD, okay, it's a linear decomposition only, but it's a generalized form of PCA. Okay, it's a generalized form of PCA. What in the case of PCA, right, when we do the decomposition, actually what will happen is this, maybe this when you read this in detail, right, you will understand it probably. Okay, this U matrix, okay, becomes equal to this V matrix, V transpose matrix, okay, which is also called as a right eigenmatrix. Okay, this these two become equal. Okay, these two become equal. Okay, so here what you do is you take the transpose of, you take the decomposition of this right matrix. They become equal essentially. So you need to find only one of them. Okay, you need to find only one of them. They are essentially equal. Okay, they are essentially equal. So you'll be doing this. They are essentially equal for a square matrix. See, PCA is, please remember, PCA is done on a square matrix. So this has to be B times B. Okay. So this will be B times B transpose. This will be B times B. This will be B times B, and the transpose would be here. The transpose would be here. Both the things are equivalent. Okay. Both the things are equivalent if it's a square and symmetric matrix. Okay. So they become equal. Okay. These two things become equal. So you have to find only one of them. That is why I'm saying PCA is the extension to SVD. PCA is done only for a square matrix. And this B cross B is nothing but called as the covariance matrix. Okay. It's nothing but called as the covariance matrix. But you have to standardize it first. If you're interested, please read about it. And then you'll be able to grasp all these concepts that you will see all these concepts like in any definition of PCA. So there is a whole theory behind it. You will see the different optimization techniques for it. Ultimately, what it will boil down to is both things will become equal. U and V transpose will become equal. So you get only one of them. Okay, you get only one of them. And how do you get U and V? You do the eigen decomposition of this or this. Both things are the same. Okay, this or this, both things are the same. Because PCA is done for a square matrix. This B cross B is nothing but the covariance matrix itself. Okay. These things are a little difficult to explain if you don't know matrix algebra and matrix calculus. And also, I would require at least 8 hours just to describe the matrix algebra part. That's why probably it's not there in your syllabus. Okay. So this is how we do using traditional decomposition. There are methods which are deep learning based. So there are deep learning models which can be used to give you a low dimensional representation. Okay, low dimensional dense representation of any data. Okay, of any data. So I'm going to describe first in the context of words. Okay, so I'm going to show you a model word2vec. So this will give you a representation for every word. Okay, this will give you representation for every word. Let's see what this means. Okay. Imagine I give you a text, okay, or there can be, say, multiple paragraphs, or there can be multiple documents. So you are given essentially a corpus. You are given a corpus, and the objective is you have to find if two words are similar or not. Okay, if two words are similar or not. Okay, from this corpus, you select any two words, and you have to tell me how similar they are. So, any ideas what could be done? Have we discussed this before to some extent? Have we discussed this before to some extent?
I think vectorization and then see the difference between the vectors.
So let's say you vectorize them, and how would you see the difference? Okay, so maybe say I'm showing you the vectorized one. So this is the encoded data that you got. Okay, so if you look at these two vectors, so the $30 and $40. So you are saying that I will compute the similarity between the $30 vector and $40 vector. Is that so?
Yes.
Okay, so you are looking at it across the corpus, right?
Yes.
You are checking, but isn't that, you are ignoring the semantic similarity of it. Yes or no? Aren't you ignoring the semantic similarity of it?
Yes, I'm doing it with calling.
Okay, because you are just essentially looking at what I would say, if they were present or absent. Yes or no?
Yes.
We are just looking at the presence and absence of a word in respective documents. I agree. This makes sense. Okay, this makes sense to some extent. But there are many things which are lost. You are not counting the frequency of the word. You are not essentially saying if these two words. Okay, what type of similarity metric would you choose? What type of similarity metric would you choose here? Through which you will figure out the similarity between them. Will you choose Euclidean, Manhattan, or cosine?
Manhattan.
Okay, for the presence and absence. Okay, but see, currently you have 100 documents. Typically in a corpus, you will have million documents. Don't you think for any two pairs, it would be almost the same?
Yes. Because
I mean, for a high dimensional data set, there would be many pairs that would share the same similarity, right?
yes.
So, isn't that, I would say, unfruitful in high dimensions?
Yes, agree.
Okay, so the idea here is we are going to use a neural network model first to project this data into a smaller space. And from that small space, I'm going to take the vectors of this $30 and $40 and will then compute the similarity. Okay, it's the same idea that we did in PCA, but now it is done using neural networks. How this neural network is trained is using this idea that, okay, let's say that if you look at a word, say king and a queen, okay, can I say that these two words occur frequently together? Yes or no? Because they describe what we say is like a royal hierarchy. Does that make sense? Can I say that words like king and queen, they are more similar than words like maybe say boy and a farmer? Yes or no?
Yes, yes.
Because they are very close. You would see them in a lot of times in the same document. Okay, a lot of times the same document. So the way these you can say the values of this say king and queen are learned, if they are occurring together in a lot of times in similar documents, it's the same concept here. But now you are looking at it from a sparse perspective. A lot of zeros and ones are there. You would be ensuring that if two words are frequently occurring together, the you can say the vectorization of those two words will be very close. Okay, the vectorization of those two words will be very close. So using this objective function and ensuring that if two words or pair of words, if they frequently occur together, their vectorizations are closer, we use a model called as word2vec. This is the resultant model, which is called as word2vec. The name itself tells you that it is going to give you a vectorized representation for every word. Now, how to make use of it? It's actually very simple. So I have, I think here, okay, just a second. Yeah. So to use this, you have to download a library called as Gensim. Okay. So install this library. Okay. See, the code for all this is kind of very specific. So I am using a pre-installed notebook. So in my case, this is already installed. Okay. So you install this Gensim. And after this, what you do, you call this word2vec model. Okay, you install this, you call this word2vec model. Do you want me to show some sample corpus in this library? So just like sklearn, there are what we say is some small data sets in this. Do you want me to show some of these small data sets? Yes, people. Do you want me to show some of these small data sets, or shall I do it on the tweets that we have? What do you recommend?
Tweets.
Okay, on the tweets. Okay, all right. But there are some data sets that are there in Gensim also that you can use. Okay, so I'm going to use this word2vec model. Okay, so calling this word2vec, it has a special syntax. Let me just copy paste this. Okay, all right. This is how you use it. Okay. So what you have to do is you have to take these texts. Okay, so your sentences are, see, if you remember, these are your texts, right? I'm going to take the, say, the first 100 texts. Okay, so these are your first 100 texts. Okay, I'm going to convert it to lowercase. Okay, I'm going to convert it to lowercase. All right, and then I'm going to use the word tokenize function on it. Okay, so let's use the word tokenize function. So let's say my data is an empty list. So for each string in this, I'm just printing it for you so you can see, okay, each string is printed. So this each string is printed, right? I'm going to apply word tokenize to it. Essentially, you can split it using what we say is the split function. I'm not doing that because split function does not work that well. So from NLTK, you use word tokenize. Okay, and split your data. So you're going to split each token. Okay. So split, okay, that's how you split. You can see that it separates everything nicely. And once you have split, okay, once you have split, what you do is you can append this to your data. That way, every tokenized string is present in data. So this is the first string tokenized. Can you see that this is the first string tokenized? Does it make sense? And by the way, this was your first string, okay? This was your first string. So it has nicely tokenized it into these individual parts. Is this clear? So I'm using these 100 individual strings. I'm showing you first you have to tokenize these strings. Once you tokenize, so this is the first one, okay, at index 1. This is the text for it, okay. So it has, split all the individual words. If you look at the second one, so data has the tokens for each of my, so data has the tokens for each of my strings. So now what you have to do is you can say your sentences is your data. Okay. The model will be trained. So here you have to pass the sentences. Okay. Let me call it, say, tokenized sentences. Okay. Tokenized sentences. Okay. So you pass these tokenized sentences here. Okay. Tokenized sentences here. This would be the length. Okay. The length here means that you are going to generate an embedding of size 10. You are going to generate for each word, you are going to generate an embedding of size 10. Window here means that you are looking at 5 consecutive words to find similarity. Okay. So basically, let's say if you want to look at this word at, you are essentially going to this window of the next 5 words. And if in these 5 words, if you find another word, so it's like, see, when we are saying that, for a pair of words, the embedding should be similar. See, I can look at the whole corpus, and then, the other way to look at it is, I can actually see for a corresponding window, if 2 words are occurring together in this window, then I say that, okay, they are similar. So if window size is increased, what do you think will happen? Will the compute time increase or will the compute time decrease? Think about it. Will the compute time increase or will the compute time decrease?
Increase.
It will increase. Okay. So if you do not provide this window size, I think the default value is corresponding. Maybe if I remember correctly, it is 10, but you can decrease or increase this as per your data. Minimum count 1 means that only if the words occur more than 1 time together, then you apply the function. So if you make it say 3, what do you think? Will the compute time increase or decrease for a pair of embeddings?
Increase.
It will. So if you increase this number, the compute time will decrease. So you are essentially saying that words are similar and their embedding should be similar only if they occur at least 3 times together. Okay. This is a hardware factor. So currently my system has 4 CPU workers, 4 cores in my processor. So you can utilize them all. Okay. You can utilize them all. So we are saving this model. You can actually save this model. Okay. 10 here denotes the size of the vector that will be generated. Okay. So it will take maybe some time. Okay. Throwing a warning. So previously it used to encrypt the data also, but now it doesn't encrypt. Okay. So this is done. Okay. This is done. Just give me a sec. Yeah. So now you can use this. And just to show you, if you want to load the saved model that you trained, so this is how you can load the model. Okay, yeah, you can say word2vec.load. You are loading the saved model. Okay, if you want to train it, you can train it on a new vector also like this. Okay, all right. All right, and now if you want to get the embedding, you just have to say this. So if you want to get the embedding, you can simply say model dot. So give me a word for which you want to get the embedding. So give me a word for which you want to get the embedding. You can actually look at any of the words. So I'll show you data and you tell me any of the words which is present in data, okay, for which you want to get the embedding. Give me any word that you see, okay, and we can get the embedding of any word. Obviously, I should have done, what we say is stop word removal and all that. I haven't done it. But for which word do you want me to get the embedding? It can be meta characters also. So give me a word for which you want to see the embedding. Any word? Okay, let's say I'm looking at this Virgin America. Okay, this is a airline. Okay, so this is the embedding for this word, the 10 length embedding. You can see that this is the embedding of length 10. Okay, and let's say I'm going to use another embedding, say airline. I'm going to use another embedding, say airline. Hopefully, airline is also a word. Okay, in this corpus. So this is the embedding for airline. And now you can compute similarity between these two words using cosine similarity. So cosine similarity would be the ideal choice, like as per my experience, but you can use Manhattan and Euclidean, whatever you prefer. Okay, so you can use cosine. So I'm using Eskilon matrix.pairwise, import cosine, it's called as cosine distances. Okay, so I'm going to use these cosine distances. So I have one side is this. Please note that you have to reshape it. Okay, so if I print the shape of this, right, it will be 10 comma. You have to reshape it as 1 comma 10. Okay. Okay, or maybe say minus 1 comma 1 if I do. So 1 comma 10, right? Sorry, 1 comma minus 1 in that case. The other one is for your airline. Let's see how much similar they are. For 100, I'm not sure because we are just using 100 documents. So it is similar by 81.89, which means that the highest cosine similarity is what? Anybody who remembers? What is the highest cosine similarity? In what range the cosine similarity is that? -1 to 1. So this is the range for cosine similarity. Okay. What we are computing is cosine distance. So cosine distance is 1 minus cosine similarity. Okay. Cosine distance is 1 minus cosine similarity. Okay, keep this in mind. Okay. So this would again be in the range of -1 to 1. This would again be in the range of -1 to 1 if you think about it. Okay. So currently they are dissimilar by, they are dissimilar by this 0.818. Okay, they are dissimilar by this 0.818. Okay, they are dissimilar by this 0.818. I mean, if it would be lower, right, then I would say that, okay, they are highly similar. Cosine distance is the inverse of cosine similarity. Basically, it is 1 minus of this. So higher the distance, more dissimilar they are. It's a positive metric. Okay, please remember this. Sorry, this is a negative metric right now. Okay, this is a negative metric right now. Higher the distance, lesser similar they are. Less similar they are. Okay. Any questions about this? You can use Euclidean distance also in the same way. Let me show you the Euclidean distance. So Euclidean distance is also a negative metric. Lower the better. So you can just pass Euclidean distances here. Same thing you can go for Manhattan as well. Okay. So this is for Manhattan. These are all negative metrics, lower the better. Okay. Please remember cosine distance is 1 minus of cosine similarity. Okay. This is important. People get confused between. See, a distance metric is always a negative metric. Higher the distance, lesser the similarity. Okay. Okay. Any questions about this? So this way you can generate the embedding of any word. Using this model word2vec, you can generate the embedding of any word. Do you want to see the state-of-the-art model also? This is not what we say is the best. Do you want me to show you the best model also? What do you recommend? Do you want to see the best one which is available across the web? Or is this sufficient?
Best one too.
Best one too? Okay. So if you want to see the best one, I mean, it will take me some time, okay, maybe say 10 minutes to download the model. So there are two ways to do it, okay. So you use a pre-trained model and get the embeddings from it. So currently what we are doing is we are training it ourselves, right? Okay. So I will recommend that you get a pre-trained model and get the embeddings from it. So you don't have to train it, because if you train it and if you do not have enough corpus, the results will not be that great. Okay. But if you have enough data, you can then train it as well and even get better embeddings. Okay. Even get better embeddings. But it will take a lot of time. You need to have at least a GPU worth 16 gigabytes or more, okay, which is typically not there. You can use a Google Colab notebook, or maybe say a Kaggle notebook. Kaggle notebook gives you access to around 16 gigabytes of RAM. Okay, you can actually get 32 gigabytes from P4 TPUs. Have you guys been using Kaggle notebooks? Is there anyone who knows about Kaggle?
Yes.
So Kaggle also gives you an environment like a Jupyter notebook. If you are not aware, okay, so I'll just show you. Okay, this is the website where you can participate in competitions. Okay, just a second. I'll just open some Kaggle notebooks. Okay. All right, so you can just create a Kaggle notebook, create an account. Okay, so this is similar to your Jupyter notebook. Environment is actually almost the same, but it gives you more access. Okay, I mean, it gives you more resources. So here you can get at least 30 gigabytes of RAM, up to 30 gigabytes of RAM, almost. Okay, so just to start this, okay. The interface is the same. If you want to create new cells, you click on plus. If you want to run something, click on this button. Okay, interface is the same. So if you are using heavy duty tasks, okay, if you're doing heavy duty tasks, you can use this. So I want you to see something. What is the maximum RAM here? Do you see the maximum RAM which is here?
30 GB.
30 GB. If you look at your Kaggle, right, Kaggle will give you around 13 gigabytes, 13 or maybe 16, no more than that. Colab will give you close to 16 gigabytes, 16 or 13. It will not go beyond. You can even give GPUs. Okay, let me just show you. So you see accelerator here. Okay, so these are graphic cards. So you can use these graphic cards also and provide these options. So this is, I believe, 16 GB graphic cards. You get 2 graphic cards. So 16 into 2, 32 gigabytes. So you will see 2 graphic cards right now if I restart this. If you want to use this P100, this is a single graphic card of 16 gigabytes. Okay, this is again a single graphic card. Okay, this is again a single graphic card that you can use. I recommend that you use this P100. P100 is relatively faster. Okay, but if you have, see, in some cases, this P4 into 2 will be faster. In some cases, P100 will be faster. Generally, in my experience, P100 is relatively faster than P4 into 2. Okay, so for whatever tasks that I have trained on, P100 was better than using 2 graphic cards. Okay, TPU I haven't really tried. It was introduced, I think, 1 year back almost. I haven't tried this, but P100 was giving me a reasonably good performance. So anything that you can train on Colab, maybe say in 4 hours, you can do it here in 1 hour, maybe 1.5 hours. So this is much, much faster. Okay, so this is just a suggestion from my side. Use this Kaggle. And so Colab gives you, I think, a session of around 6 hours. Are you aware of it? If you're using Google Colab,
Yes.
the session timings are 6 hours. You cannot use it for more than 6 hours. You have to restart the session. This gives you a session duration of 12 hours. And if you're active, it will actually get extended. Okay, if you're active, it will actually get extended. Okay, and there are a lot of other things. Okay, so just one suggestion. If you want to use, okay, I'll just show you here. So do you see this internet on and off tag here? So if you want to install something on Colab, you can do it directly with the pip command, right? In Kaggle, you have to give you have to register it with your mobile number. Okay, so typically this tag will not be shown to you. So it will show you here that, okay, please register your mobile number, and then this button will come. So I'm just letting you know right away. This tag will be off. I mean, this tag will not be even displayed to you. So first register with your mobile number. There will be a message here. So you register with your mobile number, and then you will see this tag, and you'll be able to then install your packages as well using pip command. Otherwise, pip will not work, and you guys will get frustrated. Okay, I cannot install packages. Okay, so make sure that, okay, you go through and you register through your mobile number first, and then use it. This is excellent. Okay, free and excellent resource. I recommend it wholeheartedly, even better than Colab. Maybe use it like in your free time. Okay, so I'm going to show you the state-of-the-art pre-trained model and how do you get embeddings from it. So for this, you have to install a library called as sentence transformers. Okay, you have to install a library called as sentence transformers. Okay, so let me just show you. Okay, let's get. Okay, so these are the different models that are available. Okay, there are a lot of these pre-trained models that are available. Okay, so these are the models that are available for you. You can download any of them. Okay, you can download any of them. So what this means is this, like I'll tell you about some of them. So FastText is actually multilingual embeddings. So it is trained on the Wikipedia corpus. It was trained on the news data using the subword representation, and the length is 300. Okay, the last letter that you see, it is telling you the length of the representation, the encoding size. Okay, so this is the word-to-vec model trained on Russian language, Russian corpus, and the length is 300. Okay, so I'm going to show you something which is, say, based on Twitter. So let's use maybe, say, this glove Twitter 200. Okay, so let me just use this. Let's just use this. It will take some time to download. Okay, it will take some time to download. Okay, you can see that this is quite heavy. Okay, around 700 MB, 750 plus MBs. So it will take some time, okay, for you to download. So once this is downloaded, you can get these vectors. Do you want me to stop it, or you can do it yourself? Do you want me to stop it? And you say you can do it yourself? I'll just show you a sample bit of code or like how to use it. Okay. Or maybe let's wait. Okay, it will take maybe, say, 5 minutes max. Let it get downloaded. So these are, I would say, one of the best models that are available that you can use, and I mean, get the embeddings for every word. After this, I'll show you that you can get the embeddings for the whole paragraphs also, whole sentences, whole documents. Okay, and I will probably give you a small, you can say, take-home assignment as well. I'll not be grading it, but I mean, if you are interested, you can do this. Okay. Maybe I'll describe a project, and if you're interested, you can do that. Shall we discuss the project itself first? Meanwhile, it gets downloaded. What do you recommend? Shall we discuss the project alongside? Like, it would be a nice addition for your profile. if you're interested in doing it. Okay, I'm just giving you this. So this is not a part of your GUIs project. Okay, I'm just giving you some project that you can try out. Okay, so you can actually make an information retrieval system. Okay, using these concepts. Okay, I'm going to give you basically several ideas along these lines, and you can try implementing any of them. So imagine that you are given. Is there anyone who is in academic environment right now? Is there anyone who is working for a company, or maybe say a university, or let's say you deal with say some toolkits or SDKs? Is there anyone who's like this, like who works along the same lines? No one in the participants? Okay, so let me just say this. Imagine that you have a task where I give you a search query, okay, and you have to figure out which is the command, or let's say basically it's like a chatbot. Okay, it's like a chatbot, and you're interacting with this chatbot about some toolkits. Okay, so let's say if you're working for NVIDIA, so NVIDIA has a lot of packages that you can install. So if you want to ask this chatbot, okay, I want to install this library, what should I do? So it should be able to search in the documents of NVIDIA, in the documents of NVIDIA toolkits, and it should be able to retrieve only the relevant, what we say is the text for you. Now, we already have one software which does it for us. There are many softwares which do it for us. Like, can you tell me what are the ones that you guys use? Do you guys use ChatGPT for it? Yes or no?
Yes.
You can ask ChatGPT like simple questions and it returns you. It's not accurate all the time, but it returns you, okay, this is what you can do, right? So it understands your query. So the idea here is, okay, so imagine you collect the documents from NVIDIA, okay, documents from NVIDIA. Okay. Okay, you can actually scrape all the documents. Okay, you can actually scrape all the documents from this NVIDIA website. And what you can do now is you break, so there will be PDFs, okay? The documents will be PDFs. So from each PDF, can you break it into paragraphs? This can be done, right? Yes or no? Does that make sense or not? See, there are sentence tokenizers that you can use. There are paragraph tokenizers that you can use. You can use the new line character to determine if there is a paragraph or not. Okay. So break a PDF into paragraphs. Essentially, you need a PDF parser to get the text. Okay. So use a PDF parser to get the text. Basically, use a tool, a package which can get you the text from a PDF. There are many libraries in Python that can help you do it. So I can tell you some, like PyPDF2 is there, Pika is there. You can think of this LMB unit that is also there. So I'll show you. Okay, there are many, probably 20, 30 are there. Okay, so PDF parsers. Okay, in Python list. Okay, there might be many. There might be many, close to 20, 30. Okay, so this PDF miner is also there that you can use. Okay, okay, let me show you. Okay, I mean, if you look at this link, it shows you 4 PDF parsers. There are more than 20, 30, if I remember correctly. So these are the two, these are the 4s that this one recommends. I'll show you. Okay, I actually went through a Stack Overflow page. Okay, where I saw, I mean, the list of parsers. Let me see if this is the one. Yeah, no, this is a particular one with PyPDF2. So there are many that you can use. Yeah. Okay. Second. Just a second. Just a second. Yes, sir. Okay. Do you remember there is another website like Stack Overflow, which I mean, which is similar to Stack Overflow, but gives you a lot of results. So this is another resource that you can use. This is Pi. So there is one PDF reader. There is this PyPDF, PyPDF2. Then you see this, okay, PyMU PDF. Okay, there are a lot of them. Okay, there are a lot of them. I'm unable to get to a link where it shows the comparisons with almost 20, 30 parsers. I saw it one of the Stack Overflow links a while back. Okay, I'll just do this. Okay, 1 second. So there are many people who have done it. Okay, 1 second. I'm trying to find a list of these 15, 20 parsers in one shot. Here you have PDF Miner, Tabula, PyMU PDF, Camelot. Okay, people have done it for various, tools. Just give me a sec. I think I can find that link for sure. Okay, just a second. Let me see on GitHub also. There might be a. Okay. There might be a comparison for sure. I've seen some libraries in the past which many people use. Okay. Maybe I'll get the link and share it with all of you. Okay. I've seen some GitHub links, also some Stack Overflow links where they tell you that, okay, you can use these particular ones, and they show the performance with respect to each other on a benchmark data set. So you can use any of these parsers, they will work well for you. Okay, so use one of them, get the text from the PDF parser, break it into paragraphs, and then what you can do is get the embedding for each paragraph. Okay, so now the idea is this: given a search query, you can also get the embedding for this. Okay, you can find this embedding using the model, and the last step would be like retrieve the paragraph with the most similar text, with the most similar embedding, essentially. Okay, and your job is done. So this is how you do it, like a simple information retrieval systems. So you can use pre-trained models. Okay, so for getting the embedding for each paragraph. Is the process clear? Yes, people. Is the process clear? You can actually do this for a lot of applications. So I'll give you maybe say a few more. Think that, okay, you are maybe say a conference organizer, okay, or maybe say there is an event in which some people are going to send some work for you to review. Okay, so you have a pool of reviewers and you want to know to which reviewer I should assign this given document that you have received. So essentially, you can say you have hired a lot of people, and these people have different expertise. So now you have an incoming document, and you want to know to which person I should assign. So the idea is you look at what these people have published in the past. You look at their articles, get their embeddings, and for a new article which is coming in, see the similarity between the embeddings of the documents of the reviewers that you have and the new document which is incoming. Whichever is the most similar, or whichever you can say authors are the most similar from their respective articles, you say that, okay, these are potential reviewers, and you give it to them. So you can essentially make a conference article review system or conference article review recommendation system like this. You can extrapolate it to any information retrieval system as long as the objective is to find similarity from the text. Okay. And this is how they are made. These information retrieval systems are made, especially if the data is text. Okay. Especially if the data is text. You can incorporate even extensions to it. So see, a PDF contains images. So there are tools which can extract images for you. And there are deep learning models which extract embeddings of images. And if somebody asks for an image and asks you to retrieve relevant articles, you can do that. Okay, you can do that. So given an image, you know the embedding of that image. And you have a lot of documents in which there are images. Get the embeddings of those images, match, and then you can do retrieval of similar images. So just like text, there are image embedding models also that you can use. Okay, I'm going to show you how to use these embeddings. Okay, so I think there is this function called as most similar. Yeah, so this is the most similar function. So if you want to apply this most similar function to this Twitter, so give me all the words which are most similar to the word Twitter. Okay, so it will go to its repository and will find the words which are most similar to it, and it reports the similarity. This is cosine similarity essentially. Yeah, this is cosine similarity. Okay, so these are the words on which it was trained, where the similarity is the most. Okay, where the similarity is the most. I think you can actually do it like this. If you want to get embedding for any vector, you can simply say, I think, give a word like Twitter, and I think it will give you a 200-dimensional embedding for this. This is the 200-dimensional embedding for this. This is the 200-dimensional embedding for this. Okay, so you can use it like this. So use pre-trained models to get the embeddings, and then you do similarity comparisons. Okay. So if you're interested, build an information retrieval system as one of your projects. There are several extensions to it. You can incorporate multiple modalities, images, text, audio. So you can do, say, an audio recommendation system. So let's say if you have the list of songs which a person has listened to in the past. So if you have a collection of songs, then you can do audio embeddings and find the most similar audio embeddings. You can actually look at the text of those songs, and based on text, you can make suggestions. So you can incorporate multimodal similarities to have a better recommendation system. So you can use audio as well as the text of the song. Because nowadays, you can actually have an audio file converted to text using speech-to-text recognizers. So there are many different applications, and you can incorporate it over a multitude of embedding systems. Okay, this is how the actual things are designed in the industry. Any questions up to this point? Yes, people. Any questions up to this point? Is it too much? Yes, people. Is it too much? Because I see. Okay, probably yes. Yeah, I agree. Okay, let's see how you convert sentence to a word or a paragraph to a word. So this is called as sentence to vec or sent to vec. Okay, also called as doc to vec. You can convert the entire document, okay, to a vector representation. So currently we are doing it for words, right? You can do it for what we say is the whole document or a paragraph or any combination of text that you have. You can generate an embedding for it, okay, and then you can find similarity between the text. Okay, let me just show you. So the model is called as doc2vec. Okay, here it is. So I'll just show you the whole code. So this is like the whole code for it. So I've just given some sentences. This is the first sentence, second sentence, yet another sentence. Okay. You have to break it down into tagged sentences. So for every sentence, you have to say that, okay, this is the 0th sentence, this is the first, this is the second, this is the third. So essentially, if I show you tag data, okay, this is like this. This is how you should pass the data to your model. This is how you should pass the data to your model. Okay. Do you see that it's essentially giving that, okay, the first sentence is like this, okay, and the tag is given as the number of, the integer to the sentence. This is the second sentence. You can see it has been broken down, and the tag is given as the number of the sentence. This is the third sentence. The tag is given as the tag 2. It's present at location 2. This is the third sentence. It has been tokenized. So this is what you have to pass to this model. And what it returns is the embeddings of the 4 sentences. Sorry, I have 5 sentences from 0 to 5. So these are the sentences. Each sentence is defined with the vector size as 10. Window size is 2 is the same thing. If you want to find similarity between the sentences, you're looking at similarity between the words and doing it across the sentences. This is the same, min count is 1. At least like one similar sentence has to be present, and number of workers is 4. So these are your embeddings, these 5 sentence embeddings. So if you want to get the embedding of the first one, you can simply say sentence vectors of 0. So this is the embedding of your first one. Okay. This is the embedding of your first one. You can get it for any sentence. Okay. So here you are training the model. Okay. Here you are training the model. You can actually use pre-trained models as well. Okay. You can use pre-trained models also. Okay. Just to show you. Okay. I'm going to show you how to find the sentiment of say different tweets using a pre-trained model. So let me do that. Just give me a sec. So I have a pre-trained model here, maybe somewhere. Okay, just a sec. Okay, I'll show you the pre-trained embeddings for it. Just give me a sec. Okay, you have to install this first. So install this library. This is the prerequisite. In my case, it is already installed. It is quite heavy. Okay, it's quite heavy. It takes around 1.5 gigabytes. Okay. So once you've installed it, okay, just a second. So just to show you, okay, this is how you can do it. I'm going to show you the embeddings of all the tweets. Okay. So let's say these are my tweets. Okay, so these are my tweets, just to show you. Okay, these are my tweets. Okay. Now, what I have to do is for these tweets, okay, for these tweets, I'm going to maybe select, say, the top 100 tweets and show you how they are predicted as. So I'm going to select the first 100 tweets, okay, and let's see how they are predicted as. So these are my tweets. Let's save them. Okay. So these are your tweets. So pass these tweets. Okay, 1 second. So pass these tweets here. Okay. And these embeddings will contain you can say these embeddings will contain now the representation, so I don't remember what exactly is the length of each representation using this model. There are so many models like this. Okay. Let's see what is the length of it. Just give me a sec. It will load this model, convert each model into a fixed length representation. If I remember correctly, it is 750 plus. Like the representation would be having length, with 750 plus dimensions. Let it just run for some time. Probably it will take 3 to 4 minutes. Okay, this is done. So if you look at embeddings.shape, so for each document, now I will have an embedding. I have 100 documents. Whatever is the length of each embedding, that you will see. So it's around 384. So each model has been converted to a length of 384. Oh, it's mini LM. Okay, so it's a small model, not the biggest one. The biggest one will have around, I think, 1200 plus. Okay, the length of the embedding will be 1200 plus. The bigger the embedding, better are typically the results, but it takes more time to train. Okay, and the number of parameters are more. The model is heavier. Okay, so let's say if you look at the embeddings of maybe say I want to compute the similarity of say any two tweets. Okay, let's look at some of the tweets. Maybe say I'm looking at say this tweet 3 and tweet 4. Okay, so let me get tweet 3 and tweet 4. Okay. Okay. Why don't you give me a sentence? Okay, can you give me a sentence, please? Okay, and let me show you a tweet and you make a synonymous sentence to it. Okay, I'm going to show you a sentence, maybe say this. Okay, so this is a sentence. Maybe I'll take a smaller one. Okay, so that you can okay, can you rephrase it? Can you rephrase it quickly? Okay, can I say that? Okay, Virgin America, okay, has added commercials to commercials for its customers to view. Okay, okay, not a pleasant experience. Does this make sense? I have just converted, you can say, synonymously to this. So do you see that? Okay, obviously there are some, you can say, words which are common, and there are a lot of words which are, I have misspelled it as well. Maybe say I'll just complete it. But like if I compute the similarity of this, like if you do it with the plain text example, what do you think the similarity would be? If I convert these two sentences, okay, if I convert these two sentences to say simply a representation from say bag of words, do you think they'll be heavily similar? Do you think these two sentences will be heavily similar?
Yes.
Oh, really? Why would they be heavily similar? If you use a simple bag of words representation, semantically they are similar, right? But think about when you convert them to the structured representation, will they be similar? There is only a couple of words, right? Let's say like added, commercials, maybe say experience. So only 3 words are matching, right? Or maybe 4, like the word two also. Only 3 or 4 words are matching. Okay. Maybe I'll just change it. Okay. I've added advertisements. Okay. Now, okay, let's say this Virgin America is matching. Okay. Now, if you convert it, say not a pleasant journey. Okay. Now, what would you say? Are they similar from bag of words?
No.
No, right? I have changed a lot of words, but you will see that like these models, right? These state-of-the-art models, they will say that, okay, they are still very, very similar. Okay, let's see. So I'm going to encode this sentence. Okay, that is the beauty of these like these models that you see. So I'm going to encode this sentence. Okay, this is the embedding that I get. So let's call it embedding of the sentence. Okay. And I'll also get the embedding of this as well. Okay. Okay. Let's say, okay, similar sentence. Yeah. So I've the embedding, let me call it embedding of similar sentence. Okay, let's see how far apart they are. Okay, let's see how far apart they are. Shall I compute all the distances like cosine and all that? Okay, I'm going to do everything. Okay, let's see cosine, Manhattan, Euclidean. You will see they'll be fairly close. okay, you will see that they'll be fairly close. So let's do cosine distances. Lower the better. Please remember, lower the better. Okay. So this is my embedded sentence. This is my embedded sentence. I'm going to reshape it into this 1 comma minus 1. Okay. Same thing. I'll do it for this embedded of similar sentence. Okay. Okay. No, it's even higher. Okay. Let me check. Okay. Is this cosine similarity or is this cosine distance? It's 1 minus cosine similarity. So cosine similarity is not working well. Let's see. What about, I presume that they will be quite similar. Okay. Let's see. Let's talk about, say, Manhattan distances. Okay, it seems, I don't know whether 21 is going to give me a, I mean, is it a good number or not? I'm not sure about this. Okay, maybe I'll see with respect to some other as well. You have to give me another sentence, which is, say, quite different. And then we will see. Okay. So this is your Euclidean distance because it is squared. So values which are closer, they are getting nearby. Can you give me another sentence so that we can actually compare with from very different sentence? Okay. So let's say this is sentence 1. Okay. And let's say this is sentence 2. So sentence 2, I'm going to write it as maybe like this. Say, what should we write? Okay. Okay. Excellent experience. Okay. Loved the flight. Okay. Loved the, you can say, atmosphere. All right. So I'm doing it for sentence 2 now. Okay. So this is, okay, let's see. Okay, I mean, the cosine similarity is almost the same. Okay, for both of them, it says that, okay, they are almost equisimilar. Let's see Manhattan. Manhattan is also the same. Okay. And Euclidean slightly grown higher. Okay. Okay, let me see. Okay, let me see. Okay, maybe I'll show you for a small word. I mean, it's not a small thing. Let's say not a pleasant journey. Or maybe the journey was not pleasant. Maybe this is, in my experience, I think this would have been pretty nice. Journey was not pleasant. Okay. Okay, journey was bad. Instead of saying not pleasant, I'm not sure whether, okay, let's say this is 1. Let's say I look at the difference between sentence 1 and sentence 2 first. I look at the difference between sentence 1 and sentence 2. Okay, second. So between sentence 1 and sentence 2, the cosine distance seems to be high. Manhattan and Euclidean, fairly high. Okay. Let's look at this text, and let's look at now between sentence 1 and sentence 2. This is between sentence 1. So I believe that sentence 1 should be closer to sentence 2 as compared to sentence 2. Okay. So this is cosine distance for this. This is Manhattan. This is Euclidean. Now I'm going to do it with respect to sentence 2. Cosine similarity is actually going quite far away. Okay. Cosine similarity is going actually quite far away. It says that this is actually more similar. Maybe it has the word experience. Okay, that could be the reason. Okay. Okay, Manhattan and it actually says that this is more similar. It actually says that this is more similar. So it's in this particular example, it's not working well. Okay, maybe I'll try something else. Okay, let's see. Let's see. Okay, I see 95 is kind of negative. Okay. Sorry. My bad. Okay, 95 is kind of negative. Where is this 95? So this is 95. Okay. Yeah. This is your 95. Okay. Let's say excellent website experience. Okay. Horrible website. Okay, so let me get between sentence 1 and sentence 2 first. They should be different. And then we will see the difference between, okay, this is sentence 1 and sentence 2. Now it says they are fairly close, maybe because of the word website, but let's see. Okay. Okay, Manhattan, and this is Euclidean. Okay. And now we will see the difference between sentence 1 and text. This should be similar, more closer. This should be more closer. Okay, the cosine distance is, so higher the distance, lesser the, no, it says that, okay, okay, I'll see it with respect to the other one as well. Okay, distance has increasing. Let's see it with sentence 2. This should be even more. Okay, this should be even more. Yeah, this is even more. So it makes sense. Okay, this is even more. Do you see that it makes more sense here now? Maybe see, even with similar, what we say is, I mean, similar keywords. For this example, it is doing a good job. For this example, it is actually doing a good job. With respect to this, sentence 2, okay, sentence 2 is actually further away. Okay, so you can use sentence transformers here. Any questions about this sentence transformers? Yes, people. Any questions about this? Yes, people. Please ask if you have any questions. No questions, then? All right, I'll stop here. When we meet in the next class, let's build some applications from this. Okay, and we will see, okay, whether they are performing good or bad. Okay, or if there is a need for retraining or not. Because see, currently I'm using this LLM, right? Okay, this language model. This language model may be trained on an entirely different corpus, maybe say a news corpus. So there might be a need for retraining. If I use another, you can say, model which is trained for maybe say sentiment classification, maybe that model will work well. Okay, maybe that model will work well. So it depends on what corpus on which the model is trained. That also has to be taken into account. Okay, and I'll also check that the different PDF parsers that are there, I'll add it here. Okay, the availability of PDF parsers as a link here. You can refer to it later. Okay. So try doing such projects about information retrieval systems. They will look good on your profile. Okay, this way you can explore some of these existing state-of-the-art models also. So I'll stop here. Any questions? Any other questions? None. Okay. So bye everyone. We meet tomorrow.